With ghosts looming from the shadows and a society on the verge of collapse, with World War I raging in full force, opening wounds that would take decades to heal, Germany was deeply embroiled in the conflict. The seed of darkness, which would later plunge the world into even greater darkness, was being sown. But amidst that gloom, when it seemed that all we could bring forth was devastation, someone managed to cast light through that impenetrable veil of ashes. In the farthest reaches of one man's mind, a spark of genius ignited a revolution that shook the foundations of our understanding of the universe. On November 25, 1915, before the members of the Prussian Academy of Sciences, German physicist Albert Einstein presented the fundamentals of what he called the Theory of General Relativity. A mathematical monument, an exquisite piece of craftsmanship that gifted us a new vision of reality, of the space and time in which we are born and die. Rewriting more than 2 centuries of scientific knowledge, his conception of the cosmos did not speak of an immutable tapestry where celestial events unfolded. To him, reality was a dynamic theater where the presence of matter and energy wove an invisible web, the fabric of space-time. A canvas where everything happens, curved by the mass of the bodies inhabiting it. A curvature that dictated the path of moving objects, guiding them into its domain, with an inescapable force that until then was the great unknown, the architect of the cosmos we call gravity. Einstein's great genius lay in his reinterpretation of the very concept of gravitational attraction, in how he was refuting Isaac Newton's ideas about gravity, which had almost become dogma. Under the Newtonian principles established at the end of the 17th century, gravity was a fundamental force that connected massive bodies through the attraction that holds matter together. The greater a body's mass and the closer it was to other entities, the stronger the gravitational force between them. Newton's conception of gravity allowed for the explanation of a wide range of phenomena, from the movement of planets around the Sun to the behavior of objects on Earth's surface. His theory provided an accurate enough description of gravity in everyday life to remain, for over 200 years, the strongest description of the interaction that brings order and meaning to the universe. However, something was amiss in that seemingly perfect description. Newton postulated that gravity was a force that acted instantaneously, regardless of the distance between 2 celestial bodies. The law of universal gravitation spoke of gravity propagating at an infinite speed through space. It was precisely here, exploring this inevitable consequence of the theory, that Einstein stepped in to revise and reformulate all our notions about this interaction. In the intrinsic elegance of his formulas, he had shown that as an object approaches the speed of light, its mass increases infinitely, requiring an equally infinite amount of energy to reach or exceed that speed. Einstein had established a limit in the cosmos. Nothing in space can travel faster than light. A limitation that was reshaping our understanding of how the universe behaves on a fundamental level and had profoundly deep implications. Especially because it gifted us a new vision of gravity. Rather than being a mysterious force acting at a distance, it is an interaction that travels at the same speed as light in a vacuum, emerging as a manifestation of the curvature of space-time. The bodies that inhabit the fabric shape the structure of the universe around them. Planets, stars, and everything that exists in the oceans of darkness in the cosmos follow paths determined by that curvature. Gravity was not a force. It was the physical expression of disturbances in the foundations of reality. Einstein had just opened the door to a new era. Through invisible and inescapable gravity, a new chapter in human history was beginning to be written. gravity is the architect of the universe, able to bring order and meaning to a realm that, without it, would live in eternal cosmic anarchy. And with the theory of general relativity, for the first time in history, we had deciphered its most fundamental origin. It was time to listen to what that gravitational symphony was whispering to us from the depths of space and time. Einstein's equations, in their intrinsic elegance, concealed a new conception of the universe, connecting the mathematical world with the physical one with a grace worthy of a genius. General relativity forever transformed our vision of space and time. But at first, neither he nor anyone else was aware of the dark secrets lurking within his formulas. The life of a star depends on the delicate balance between two forces: gravity, pulling the star inward toward its core, and nuclear reactions, with their heat and energy pushing outward. In this fleeting dance, for millions of years, the balance is maintained. But sooner or later, a point of no return will be reached. At that moment, in the depths of the God of Light, the war between the two forces begins. When a star begins to exhaust its fuel, and the battle between gravity and nuclear power is unleashed, a hell emerges. A hell to which Einstein could travel through his equations, reaching the end of a story whose outcome was already written, with gravity emerging as the victor of the war. Nothing could prevent it from collapsing inward toward its core. A collapse that in the largest stars, with an unimaginable gravitational force, could tear apart the very fabric of space-time. The mathematics were describing the tragic death of a star, with its ashes compressed into an extremely small volume. A corrupted core with a gravitational field so intense that nothing, not even light, could escape its pull. Space and time collapsing into an infinitely small region. The architecture of the cosmos fractured at a point. Inevitably, from the equations emerged an invisible monster with the power to drain all light from the universe. Guardians of darkness, hiding at their core the place where all paths end. A realm stripped of all dimensions, a singularity where the laws governing the behavior of the cosmos collapse, where the indescribable quantum effects of gravity reign. Aware of the dark place to which the mathematics were leading him, Einstein realized that such cataclysms should have a profound effect on the very fabric of reality. Objects so massive would have the power to create disturbances in space-time that would propagate throughout the universe in the form of waves. The foundations of nature shaken by an inconceivable force, capable of trembling the pillars of space and time. Like waves surging across the dark oceans of the universe on a journey to a shore they can never reach, Einstein had just conceived the existence of what would be named gravitational waves. The last great prediction of the theory of relativity. Invisible disturbances navigating the seas of a vacuum we thought should live in calm. Waves of gravity born from destruction. Waves traveling in nothingness, as space-time itself fluctuates. The foundations of nature trembling upon themselves. Their mathematical inevitability was so firm that in 1916, just a year after the presentation of general relativity, Einstein published a paper predicting the existence of these gravitational waves. He mathematically demonstrated that certain types of mass movements in the universe should be capable of generating these gravitational disturbances. A purely theoretical work showing that these waves of gravity would be produced by rapid changes in the distribution of mass and energy in space-time. Gravitational waves that, after traveling for millions of years from the farthest reaches of the cosmos, where stories of destruction are written, would reach us as a faint whisper imprinted in gravity. Despite laying out the theoretical basis for their existence, Einstein believed that these gravitational waves would never be detectable experimentally, a feeling that virtually the entire scientific community shared. For decades, gravitational waves remained a mere mathematical curiosity, until someone came along determined to perceive those echoes in space-time, to begin the odyssey of hunting gravitational waves. Despite being Einstein's last great prediction, a holy grail of general relativity that would definitively prove the model was correct, scientists had accepted that detecting gravitational waves was technically impossible. But little by little, that paradigm began to fade, thanks to monsters whose existence we had denied for decades. In 1964, astronomers detected a strange source of X-rays 6,000 light-years away, which they named Cygnus X1. The radiation appeared to be coming from a massive star, a god of light orbiting around something invisible, hidden in the shadows of space and time. Only a few bodies, which until then were considered a fiction arising from playing with Einstein's equations, could be behind this phenomenon. The echoes of what had been recently named black holes were sounding for the first time. Beasts capable of destroying worlds, draining light, and stopping time were signaling their existence. The findings at Cygnus X1 caused a deep divide in the scientific community. Something was roaring from the depths of the galaxy, a powerful source of radiation that, at its heart, hidden from us, might be concealing an entity Einstein had unconsciously predicted during his imaginary journey to the collapse of a massive star. Many were reluctant to say that what lay in that place was a black hole. Others believed that sooner or later we would find the evidence needed to prove the existence of Einstein's darkest and most terrifying prediction. And a few saw it as a beacon of hope, reigniting the quest for that gravitational symphony. Shortly after the discovery, American physicist Joseph Weber embarked on an innovative project that many of his contemporaries deemed absurd. He was convinced that technology had advanced enough to make the impossible possible, to capture the faint echoes in the ocean of the universe. Weber aimed to develop the first gravitational wave detector in history. In his 1916 paper, Einstein had explained that incredibly massive objects accelerating at nearly the speed of light would generate these disturbances in space-time, which would propagate throughout the universe, deforming the fabric of the cosmos as they traveled. The hypothetical merger of two black holes, then considered mere speculation given that the existence of such entities had not yet been confirmed, was a scenario that could give rise to powerful gravitational waves. A battle between two monsters that would shake the pillars of space-time, creating ripples in the fabric of reality that would eventually reach us. Cygnus X1 was a signal, the universe calling to us from the heart of darkness. We were on the verge of proving that the beasts existed, and with that, a new window into the cosmos was opening before us. All we had to do was listen to what space-time was telling us. With this ambition, Weber proposed a method for detecting these gravitational waves using what he described as a resonant bar. He believed that the waves generated by violent cosmic events, such as a black hole merger, after traversing the vast distances of the universe, could physically deform a sensitive metal bar, causing detectable vibrations. He had just founded the field of experimental gravitational wave research. The theory stated that the moment a gravitational wave passed through Earth, causing space to expand and contract due to the wave-like motion imprinted on its architecture, the metal bar would stretch along with the space. Afterward, it would return to its original state, but leaving behind a faint vibration in the metal, as if something invisible had struck it. Weber sought to detect that reverberation, which would signal the encounter with a gravitational wave. The resonant bar was a cylindrical aluminum device made with high purity and cooled to extremely low temperatures, close to absolute zero, to achieve the necessary sensitivity. By immobilizing the atoms that made up the bar as much as technology allowed, Weber minimized the thermal vibrations that could interfere with the detection of a potential wave. Placed inside a near-total vacuum chamber to eliminate any external influences, he patiently waited for the echoes of a cataclysm, imprinted in gravity, to strike it. They were waiting for the arrival of a gravitational wave that would mark the dawn of a new era. For years, Weber and his team built several detectors to have multiple independent sources, ensuring that their results, if positive, would be reliable. And although the vast majority of the community believed he was chasing shadows, that the hunt for gravitational waves was nothing more than a utopia, in 1969, he shook the foundations of the scientific world. Against all odds, Weber published a paper claiming to have detected vibrations in his devices consistent with the passage of those space-time disturbances. The physicist was announcing the discovery of gravitational waves. The article generated massive media attention. Many were skeptical from the beginning, seeing that the signals he claimed to have detected were not consistent with theoretical predictions, as they were too intense. These doubts led more than 20 independent groups to replicate Weber's experiments. Everything pointed to the idea that we had been too optimistic, that the dream of detecting those whispers of gravity was destined to remain impossible. After 2 years of replicating the experiment, none of the 20 teams detected anything. Likely external interference or technical issues were behind Weber's hopeful results. The community questioned the validity of his study, and a real detection of gravitational waves was ruled out. But once again, the universe gave us a sign. Something from the darkness told us not to give up. After years of speculation and controversy, the final chapter in the story of Cygnus X1 was written in the spring of 1971. Measurements of the star in the system definitively showed that it was orbiting around that invisible object with a period of just 5 days. A speed that could only be explained if that unknown body had at least 6 solar masses. The evidence we had been searching for over decades was finally before us. There could be only one culprit. What was hidden in the darkness was a black hole. Like a dark well in the universe, everything is drawn by the gravitational tyranny of its singularity. That place where physics collapses, faster and faster, like a river accelerating in its course. With each passing moment, escaping the current becomes more difficult, until there comes a point where it no longer matters how fast you swim. A waterfall has formed in space-time, a point of no return, a place where nothing, not even light, can escape, an event horizon that symbolizes the purest representation of a boundary between the universe we know and the one hidden within the unknown, dark heart of a black hole. A beast that, while devouring the blue supergiant star accompanying it in its binary system, caused an intense accretion process. The extreme gravity of the black hole trapped material from its sister star, which inexorably spiraled toward its depths. A turbulent path where the gas heated to extremely high temperatures, thus creating that bright source of radiation. 6,000 light-years away, we had captured the first evidence of its existence. They had always been hidden under the shadow of their darkness, but we had found them. Black holes were a reality, and with them, the notes of a new instrument played in the symphony of the universe. Knowing that monsters roamed the oceans of space, there was no doubt that somewhere at some point these beasts had and indeed have gone to war. The mergers of black holes were inevitable, and therefore if Einstein's theory was not built on a lie, gravitational waves had to be coursing through the seas of the universe. They had to be out there, among us. It was our choice to seek them out or remain blind. After what was already considered one of the greatest discoveries in history, a new hope in the field of experimental gravitational wave research emerged at MIT through the mind of a young professor named Rainer Weiss. Gravitational waves were like a kind of cosmic DNA, carrying an imprint of their origin on space-time. Until that moment, we had only witnessed that fabric in calm. The surface of a tranquil ocean. With them, we would see the sea roaring, a tempest in the eternal oceans of the universe. Although invisible to our eyes, gravitational waves carry messages from the monsters that generated them. The more massive the entity and the faster it moves, the larger the disturbances in the sea. At their birth, they are incredibly powerful, pure space trembling, capable of destroying worlds and distorting time. But like waves in a pond, their strength and size diminish with distance. The farther they travel, the weaker and fainter they become, to the point where, after traversing hundreds of millions of light years, they shrink to waves smaller than an atom. Detecting them then required technology that understandably seemed impossible, hence the failures of Joseph Weber and all those who replicated his experiments. The American physicist knew that if we wanted to perceive these gravitational whispers, we needed to build the most sophisticated and sensitive instrument in the history of humankind. Fascinated by the prospects of success, Rai spent a summer developing the physical foundations of a facility that was christened LIGO, the acronym for Laser Interferometry Gravitational Waves Observatory. A gravitational wave observatory that would consist of a megastructure. An unprecedented feat of engineering. From the heart of the facility, two enormous arms would emerge, each 4 kilometers long, perpendicular to each other, and with mirrors placed at their ends. The operation of LIGO would be based on laser interferometry, a technique that uses split beams of light that are later recombined to detect small changes in the length of the interferometer's arms. This principle was what Rai believed could work the magic. When 2 synchronized beams are fired through the vacuum tunnels within the arms, under normal conditions, they return to the detector at the same time. The 2 beams of light cancel each other out because they have the same wavelength. No light, no measurable signal, just a pattern of constructive interference at the detector. However, if a gravitational wave were to pass through our world, it would distort space-time and slightly change the length of one of LIGO's arms. The very contraction and expansion of the fabric of the universe would create a difference in the distance the light travels in the 2 arms. Thus, when the laser beams are recombined, destructive interference between them occurs, an altered pattern that could be detected by photosensitive sensors. The passage of an invisible and undetectable gravitational wave to our senses, converted into a light signal that would prove the existence of these disturbances in the pillars of reality. The interferometers had to be designed to be sensitive enough to detect changes in the length of the arms. With that, with the vacuum inside the tubes, with no air molecules to affect the laser's path, the only thing that could alter them would be the passage of a gravitational wave. But to have that sensitivity, knowing how weak the expected gravitational waves would be when they shook the foundations of space-time, LIGO had to be capable of detecting changes in the arm's length 1,000,000 times smaller than an atom. We had to break through all the boundaries nature had set before us. For the detection of a gravitational wave to be possible, we would have to measure changes in length on the order of 1,000th of a proton. It's hard to contextualize what this meant, but one way to understand it is that it was like measuring the distance between Earth and Alpha Centauri, which lies 4.3 light-years away from us, and being able to say that this distance had shifted by the thickness of a human hair. These were the scales at which LIGO had to operate. Rye finished his proposal in 1972, only to begin a turbulent journey to secure funding for such a wild project. At that time, scientific research in the United States was largely funded by the military, and in the context of the Vietnam War, no one in high places had the slightest interest in the hunt for something as exotic and militarily useless as gravitational waves. However, slowly but surely, he gained more support within academic circles. From Caltech, Kip Thorne and Ronald Drever joined his crazy ambition. Detecting those gravitational waves would tell us so much about the fundamental nature of the universe that no matter how great the obstacles, the journey was worth taking. Against all odds, enough remarkable individuals saw the brilliance within the madness. Years after the idea had emerged in Rye's mind, in 1989, the National Science Foundation, NSF, took the enormous risk of funding the project. With a budget of $1.1 billion, the dream of listening to the symphony of the cosmos was finally going to materialize. After years of planning, the construction of LIGO began in 1994, marking the start of an odyssey to turn what had once seemed like a mere mental exercise into reality. A megastructure composed of 2 observatories separated by 3,000 kilometers, 2 twin facilities, one in Livingston, Louisiana, and the other in Hanford, Washington. The duplication of observatories would allow for the identification of false detections caused by instrumental failures or local effects. The sensitivity was such that even minor seismic vibrations or the engine of a nearby car could generate false positives. With 2 observatories so far apart, if they picked up a signal at the same time, they could be certain they had found what they were searching for. But this duplication was just the first layer of security. Each facility was an exquisite piece of craftsmanship, ensuring the sensitivity they required. The mirrors in the interferometers became the purest objects ever created. There could be no impurities in the crystals. Such was the work behind their perfection that each mirror cost $250,000. Simultaneously, they needed a laser unlike any that had ever been built. A laser capable of sending incredibly stable beams of light over a 4-kilometer path. This was the first obstacle they faced. The second major challenge for the engineers was that the entire installation rested on the Earth's surface, exposed to vibrations. Although imperceptible to us on the scales at which it would operate, seismic activity anywhere in the world, ocean waves crashing on shores hundreds of kilometers away, trucks on state highways, and even people walking in nearby towns generated noise that could drown out the signal of any gravitational wave. To filter all this out, they developed the high enhancement mode pneumatic isolation system. A series of pillars supported the chambers housing the components. If the ground moved microscopically in one direction, HEPI would automatically shift the chamber the same distance in the opposite direction. This ensured that the mirrors remained in the same relative position to the tunnels. The third obstacle, however, was that the mirrors themselves could be a source of noise. If they vibrated, any signal would be drowned out. To enhance their stability, silica suspensions were developed, unlike anything seen before. The mirrors would be suspended by these microfilaments with a diameter in the micrometer range. Held by threads so thin they couldn't be seen with the naked eye, making it seem as if the mirrors were floating. With this, the natural limitations were overcome. The most perfect laser ever created, impacting on the purest crystal mirrors, suspended by invisible filaments, with the tunnels resting on a mobile platform that counteracted the Earth's slightest movements. All of this, they hoped, would allow them to perceive those gravitational waves rippling through space and time. In 2001, the first version of LIGO was completed, operating until 2010 without detecting gravitational waves, but allowing for calibrations and adjustments to plan for the final version. The observatories were dismantled, and upgrades were completed in February 2015 with advanced LIGO. With it, more than 40 years after the idea that changed everything, Rai had realized his dream. Humanity had raised the temple of gravity. By late summer 2015, all reviews were complete. Before officially starting the observation period, advanced LIGO underwent a final testing phase. But within just 2 days, the universe gifted us what we had been dreaming of for so long. At 4:50 in the morning on September 14th, LIGO's computers registered a spike in the data from both observatories, in Livingston and Hanford. A signal lasting 1/10 of a second, which sophisticated algorithms quickly identified as the expected signature of a gravitational wave. That Sunday morning, the team received automated emails alerting them to what had just been recorded. The signal matched a black hole merger. They knew that if the hearts of two dark beasts had merged and generated gravitational waves, we would capture a specific pattern of increasing frequency and amplitude, followed by a rapid decrease after the formation of the resulting black hole. That was exactly what they were seeing. A perfect match between the theoretical predictions and what LIGO had observed. Many felt it was too good to be true. When they hadn't even officially begun the observation period, they had captured the most perfect signal imaginable. They were on the verge of concluding a century of speculation, fulfilling the dreams of all those who had fantasized about the day we could hear the universe's secret symphony, proving that we had turned the impossible into reality. Both in Louisiana and Washington, the same signal had been detected simultaneously, with only a 10-millisecond difference, precisely the time it takes for light to travel the distance between the two observatories. There were no doubts about its authenticity. It was a message from nature imprinted in the fabric of space-time. Keeping the discovery secret for 5 months, tirelessly analyzing the signal and the conditions at LIGO that morning in September, to rule out any manipulation or even a hack of the systems, the team was finally ready to tell the world what we had heard from the depths of the cosmos. After decades of uncertainty, with the odyssey of gravitational waves becoming almost mythical, two dark lords roaring from the far reaches of space and time had gifted us a score imprinted in gravity. We had touched the fabric of space-time, perceived a tremor in the pillars of reality from a cosmic battle. Gravitational waves had been discovered, and with them, Einstein's last great prediction was confirmed. The LIGO team held a press conference in Washington on February 11, 2016, to present the findings of gravitational wave detection, explaining its significance and the impact of the discovery on physics and astronomy. The scientific community received the announcement with great enthusiasm, as it opened new opportunities to study the universe on an entirely new scale. Immediately hailed as one of the most important milestones in the history of physics, the discovery broke through the media barrier and generated widespread public attention. Major news outlets covered the event. The news spread rapidly on social media, turning gravitational waves into a global conversation, an impact worthy of the achievement humanity had reached. On September 14, 2015, Gravitational waves from two black holes that had collided 1.3 billion years ago in a distant galaxy passed through Earth at the speed of light. They traveled through you and me. We were all stretched with spacetime by a trillionth of a meter, or 10 to minus 21. That's a decimal point, 20 zeros, and then a 1. It may have arrived weakly, but it wasn't always so. To understand what LIGO had perceived, we had to travel back to the beginning of that score. To witness the Battle of the Dark Kings. At the edge of the universe, where the boundaries of space and time blur into a dance of death and devastation, two kings emerge from the shadows to claim their rightful throne. 1.3 billion years ago, in the darkness of a galaxy far from our island of light, the cosmos bore witness to nature's most devastating spectacle. Two black holes entwined their destinies, drawn together by their inescapable gravity. A final act in the story of two princes, battling to become the lords of darkness. In a celestial fusion, through a violent and majestic dance, the two monsters orbited each other, gazing upon one another as they drew their hearts closer to that place where all paths end. Two beasts, 29 and 36 times the mass of the Sun, condensed into a space barely 150 kilometers in diameter, defined by the absence of itself. Pure space-time, warped to the limit, unleashing a storm upon the pillars of reality. In a spiral towards that tragic final embrace, the black holes moved faster and faster. Hundreds of orbits each passing second. A tempest that began to disturb the space-time around them. Like hammers on a drum, gravitational waves of increasingly higher frequency began to emerge, squeezing and stretching the very fabric of reality, a forewarning of the outcome of this dance of shadows. Until finally, in that paradoxical silence of the void, the two beasts collided. The corrupted hearts of the black holes fused, unleashing a hurricane in the fabric of reality. At that moment, as the war ended and a new guardian of the darkness emerged, that place shone brighter than the entire universe. The fusion of the black holes generated for a tiny fraction of time more energy than all the stars in all the galaxies of the cosmos. Everything was eclipsed by the Battle of the Kings. The dance had ended. A new king now ruled the shadows. But the storm was still alive, for it had not only released light. The collision transformed 18,000 trillion tons of matter into an explosion of gravitational waves. A deep disturbance born of that fatal embrace, spreading in all directions, traveling at the speed of light across the oceans of the universe, carrying information about that story of destruction and creation. Silence had returned to the Empire. All that remained was the echo of war. Invisible, but transformed into messengers of the beasts, the gravitational waves continued their journey through the vastness, crossing the seas of space and time, until finally, 1.3 billion years after they emerged, and so faint that they were now only a memory of their former majesty, they reached the place where the universe was capable of understanding itself. In the midst of their eternal journey through the overwhelming vastness of the cosmos, we were able to read that score imprinted in gravity. We had deciphered the message. The echoes of a battle between two dark princes that occurred in a place and time long, long ago. That gravitational wave had opened the door to the universe's deepest and most violent secrets. For the first time, we had heard a storm roaring in the very fabric of space-time, one of the greatest discoveries of our era, for we could now not only see the light of the universe, we were able to hear it, to perceive the notes of a gravitational symphony that would tell us the story of everything that surrounds and shapes us. In that temple of gravity, a new age had begun. As expected, given the implications of the discovery, the three principal leaders of the LIGO project, Rainer Weiss, who had started it all in the 1970s, Kip Thorne and Barry Barish, were honored for their contribution to the field of astrophysics with the Nobel Prize in December 2017. The announcement marked a moment of great emotion, not only for those involved in that dream that once seemed impossible. The entire scientific community celebrated their success. The Nobel Prize was recognizing both the historic discovery itself and the tireless work over decades that led to the birth of LIGO. The Swedish Academy acknowledged the transformative impact that gravitational waves would have on our understanding of the cosmos. The seed of a new era in astronomy had just been planted. Now that we had heard the notes of the universe's symphony, it was time to delve into it, to follow the rhythm of that melody to the darkest corners of space and time, to dance alongside the monsters.